So here are a few additional slides that is commented with the supplementary. So these slides are taken from Professor Che here. So from his class, I took some additional slides that explain the operation of backpropagation quite nicely. So if you like the description, you can take some time and try to increase your understanding towards the algorithm. But at the same time, where I would like to focus on this example, by going through this example together, where we'll try to explain how the backpropagation is actually working. So here is a architecture. So we are going to consider this architecture today, and we are going to assume sigmoid function is used for every activation. So for each unit, there are aggregation and activation. So sigmoid is used. And in the output unit, also there is aggregation and sigmoid. Aggregation, sigmoid. And where initialization is needed. So we are going to assume you have set a weight value is assigned like on the screen. So this is randomly assigned. And where we are going to assume there are only one data instance. So where this instance has two elements for the input, two elements for the output. So input vector 0.05 and 0.1, that is only single instance. And output vector 0.01 and 0.99. That's again single instance paired with the x. And last class we talked about feed-forward process. And this is using the model. So feed-forward, in other words, that is called as a forward pass, where you're simply sending the signal from the input side to the output side. So what you're going to do is, based on these two values, along with the bias value, you're going to update next layer. Then you're going to update the following layer. So in order to do that, you first want to compute the total net input to H1. The total net input is simply linear weighted sum of the input. So W1, X1, W2, X2, and bias. So you can write down the actual number like this. And if you do the algebra, then you can get the result. And then you can calculate the output of H1. So this is again perceptron. So you first want to aggregate the input signal, and then you're going to attach the sigmoid function. So the net input value over here goes into the sigmoid function. And if you simply calculate the sigmoid, then you can obtain this output. So this is the output of H1. And you're doing the same thing for H2. So the input is the same, only the difference is the weight value. So here you're going to take the combination of W3, X1, W4, X2, and B2. So 0.25 and 0.05 and so on. So by doing simple algebra, you can get the net input value to H2. This is the net input, and you're going to plug into the sigmoid function, and this is the outcome from H2. So we have the value. So the signal comes out from here, and we have one additional bias term. And then we are going to move on. So now we are going to look at the output layer. So what we worked on was hidden layer. And from now on, we are going to work on the output layer. So the output layer Y1, again, you are going to get the net input to Y1. So that is W5 multiplied by output of H1, W6 multiplied by output of H2, and B3. So you collect all the numbers and do the algebra. And put this into the sigmoid function or activation function, and this is the final outcome. So at the first iteration, this is your prediction. And now let's move on to Y2. So Y2 gets W7 output of H1, W8 output of H2, and B4. So collecting all the numbers and do the algebra. plug in and get the output of y2. So using the initial random weight value, well, you can simply plug in the input value, then you can get the prediction. So well, this is exactly same as the prediction algorithm, at the same time half of the backpropagation algorithm as well. So for prediction, you want to do feed forward or forward path. And for training, you want to do forward path and backward path as well. So the algorithm itself, so backpropagation algorithm itself, that is for training, and backpropagation again include the prediction part in it. So each time you want to do prediction, and based on the prediction result, you do backpropagation. So we will see that idea. So forward path gives me the prediction value. So y hat, y1 hat, and y2 hat. And after you get the prediction value, you can compare those prediction together with your ground truth or true outcome. So compare with y hat. Well, if you do so, you can get the error. And based on the error, you are going to update W. So that's the idea of backpropagation. So we'll see how to do it. So like I mentioned, we want to calculate the error after you get the first prediction. Here we want to assume squared error function. So it is going to be simply the difference between my prediction and the actual output. And you take the square of it, and we multiply it with 1/2. And there is a reason why we are adding 1/2. So eventually we are going to see some cancel out effect. So intentionally we are adding 1/2 to the loss function over here. So we'll see where this actually makes the computation easier. So we can calculate the loss at y1 and loss at y2 using the loss function we defined above. So since we know the actual outcome, so actual outcome of y1, my prediction. So doing that gives me this error, and actual outcome minus my prediction, giving that the error at y2. And then we can calculate the total error. The total loss is simply adding these two. So this is my error. And now we are going to reuse this error or loss value to update W. So the update is done from the back to the front. So we are going to first update the W associated with y1 and y2. Then we are going to move on to the hidden layer. And then we are going to update the W associated with H1 and H2. So let's start it. So starting at Y1, Y2, well, what we want to do is we want to measure how much change in this W5 affects the total error. So how much change in W5 affects total error? That is represented in terms of this partial derivative. So you take the derivative of loss total in terms of with respect to W5. So that's the idea. But doing this is not straightforward. So what we use here is the chain rule. So W5 is here, and total error is the summation of loss 1 and loss 2, loss y1 and loss y2. And if you consider the relationship between these two, well, loss total includes one of the term y1, and W5 only affects y1. And loss y1 is affected by the output of y1. And output of y1 is affected by the net input value of y1. Now finally, net input value of y1 is affected by W5. So the backpropagation is going backwards against this direction. So we want to get the effect of W towards loss total. We are going to calculate that this direction. The way we do it is actually using the chain rule of those derivative. So let's remove all the handwriting, and we can rewrite this partial derivative of loss total with respect to W5 in this way. So loss total sort of prime partial derivative of loss total with respect to output of y1, and partial derivative of output of y1 with respect to net value of y1, and partial derivative of net value of y1 with respect to W5. Well, if you do so, you can get the value representing how much change in W5 affects loss total. So again, loss total was calculated in this way. So square the error on y1 and y2 separately, and you take the sum. And now start from the first factor. So we want to calculate the first factor that represents how much does loss total change with respect to output of y1. So now it is all calculating the derivative. So partial derivative of loss total with respect to output of y1 can be computed in this way. So you need to review it and you need to understand this process. So this is basically taking the derivative of this guy with respect to output of y1. And if you plug in the actual values to it, so where we know what is output of y1 in the previous step, feedforward step, and we know the actual value of y1. So we can calculate this subtraction. So at the end of the day, the first factor has this quantity. The second factor here, partial derivative of output of y1 with respect to net value of y1. Where output of y1 was actually the sigmoid value of the net value. So we can represent that in this way as well. Or simply that is the sigmoid of net input of y1. One thing you want to memorize is this. So sigmoid, derivative of sigmoid has a simple form. So if you take the sigmoid prime, then it's going to be equivalent to sigmoid value itself multiplied by 1 minus sigmoid. So if you want to look at the detailed derivation, please click on this, then you will see pages of derivation step. But at the same time, you can simply memorize the derivative of sigmoid function. So this will give me output of y1 multiplied by 1 minus output of y1. Since we know the output value of y1, we can plug them in, and this is the value for the second factor. Now let's move on to the third one. So this third factor, this one can be represented as a simple weighted sum, right? So that is net income, net input. So that is simply linear weighted summation of all available value from the previous layer. So if you plug in this into here, you can simply take the derivative of this with respect to W5. So since there's no W5, these two are gone, and this will be 1. You only have output of H1. So simply taking the output of H1, that is the quantity for the third factor. So let's plug them in and let's put them all together. So in the previous slides, where we first come up with this quantity, then we could come up with the value for this. And finally, we could come up with this value that is output of H1. So if you take the multiplication of these three factors, then you can get the gradient value at W5. Since we know the gradient value, we know the update rule for gradient descent. So update rule of gradient descent, this is current W5, and this is running rate. Well, here we are going to assume running rate is simply 0.5, and this is the gradient. So if you multiply the gradient with the running rate and take the subtraction against the W5, you can get the updated W5 value. So based on my current error, the next correct value for W5 is the subtraction between this, and this is your new W5. Likewise, you can calculate W6, B3, W7, W8, B4. So you can calculate all of them. And if you calculate, you can obtain these values. So all these are the W value for the next iteration. So far we calculated this much. Now we want to move on to one previous step. So we want to calculate the values for W1 to 4. And in order to do that, we want to figure out the changeable total loss with respect to the change of W1. So, calculating this is not straightforward. You can again use the chain rule. So we can sort of expand the original partial derivative like this. So loss total with respect to output of H1. Output of H1 with respect to net input of H1. Net input of H1 with respect to W1. And the same is represented in terms of the diagram in this way. So initially we came up with the total loss, and total loss is the aggregation of these two individual errors. And W1 is affecting the net input of H1. Net input of H1 is affecting the output of H1. Output of H1 is affecting the loss at Y1 and loss at Y2. So that means when you want to do backpropagate, we want to consider multiple channels like this. So in terms of backpropagation, we want to calculate the error in this direction, error in this direction, error in this direction. So essentially, this chain rule expansion is rotating this. So the first factor is representing the error from the output layer to the hidden layer. The factor in the middle, this, and the last factor is this. So given that, we can try to calculate each factor one by one. So first of all, the loss total is the loss of Y1 and Y2. So we are going to separate these two and calculate them separately, as we see in this sort of illustration. So in terms of calculation, let's calculate the first one first. Again, this is loss of Y1 with respect to output of H1 that can be expanded using the chain rule like this. So loss of Y1 is changing along with the net input of Y1, and net input of Y1 is also changing along with the output of H1. So we are going to take these two. So the first factor, partial derivative of loss at Y1 with respect to net input to Y1. Again, this can be expanded in this way. And for these two vectors, we already calculated these two values in the previous step. So by plugging them in, you can get the quantity. The net input at Y1 with respect to output of H1, this can be rewritten using the weighted sum and output of H1, that's over here. So the remainder becomes 0, and it will end up as W5. So simply take W5 value. So the first factor is sort of computed already by multiplying what we just obtained. This is going to give us the first factor. Over here. And in the same way, you can calculate loss at Y2 with respect to output of H1. So this guy can be calculated in this way. And finally, we can get this one in the yellow box. So by simply taking this addition, you can get the quantity of the first yellow box. Let's move on to the second factor. Second factor is the partial derivative of output of H1 with respect to net value of H1. So again, output of H1 is the sigmoid, and we know the derivative rule. So that is sigmoid together with the net value. So if you take the derivative, where output of H1 multiplied by 1 minus the output of H1. So plugging in those quantity that we know from the previous calculation, you can easily get this quantity. So that is the value for the second vector, one in the yellow box now. And move on to the third vector. Well, this guy is again rather simple, so we know the aggregation formula for net value of H1. So simply take them. And we want to take the derivative with respect to W1. There is no W1, there is no W1, so turn to 0. We only have X1 left. So simply taking the X1 value, that's going to be 0.05. So by putting it all together, where we calculated the partial derivative of loss total, partial derivative of output of H1, partial derivative of net value of H1. So this gives me the gradient at W1. So now we have the gradient value. We know how to update W1. So again, this is my current W. And this is updated W1. Running rate and the gradient value. So simply plugging them in, you can get the new W value. So likewise, you can do the same for the remaining weight value, and you can get W2, B1, W3, W4, and B2. And the result of the calculation is like this. So you pass through the first iteration of backpropagation. So after you do so, you can plug in the W value or weight value, like on the screen. And the data does not change, right? So you can plug this X value to the model. That is actually the prediction, and at the same time, that is the start of the second iteration of backpropagation. So plugging them in, where at the hidden layer, you could get these two values. And plug them in, at the output layer, you could get these two values. Well, let's record that the outcome we want to have is 0.1 and 0.99. Well, 0.01, y1, 0.99. Well, compared to the value that you could get from the first iteration, well, this guy is closer to the true value. And this guy as well, compared to the value from the first iteration, what you could get from the second iteration is closer to the true value. That means if you calculate the loss will be reduced. And like this, you are gradually moving the W value so that you can eventually get some value very close to the actual outcome using the model. So if you do the same, 10,000 times, you can get this value for Y1, this value for Y2. So this is illustrating how the backpropagation is working. So each step, you're making small changes using the error and sort of spreading out the quantity of the error to tweak the individual W. So what we are doing is making small jump from some point in the graph to the point where the loss is minimized. So this is the illustration of backpropagation, and we were looking at the step-by-step calculation of gradient descent actually.